Welcome to Your Math Explained, where we make math simple and clear. My name's Angela. Today, we're stepping up our skills with intermediate level trig equations, the kind where the solution isn't just apply inverse trig and done. These equations require you to recognize hidden identities, spot quadratic structure in the skies, and occasionally use identities to rewrite everything in terms of a single function. Before we get started, if you haven't subscribed to the channel, make sure you do so that you don't miss out on new weekly content. So let's start with something not too complicated. Here we have cos 3x is equal to 1 over root 2. Seeing this 1 over root 2 tells us that it's the 1, 1, root 2 special triangle. So the first thing we're going to do is we're going to replace our 3x with theta. So we're going to have cos theta is equal to 1 over root 2. And this is us doing a substitution where theta is equal to 3x. And this is just so that it looks a little bit simpler. Now this tells us that our reference angle, theta r, is going to be equal to pi over 4. And since cosine is positive, that means we're going to be in either quadrant 1 or quadrant 4. So that means we're going to get theta is equal to pi over 4, which would be in quadrant 1. And then in quadrant 4, we would get 7 pi over 4. Now we go ahead and do our substitution back. Since theta is equal to 3x, we're going to get x is equal to, the first one is going to be pi over 4 divided by 3. So that'll be pi over 12. And then our second solution is going to be 7 pi over 4 divided by 3, which is going to be 7 pi over 12. Now we're not done yet because our domain here is x is between 0 and 2 pi. And if you recall from transformation, we have cos 3x. So our b value here is 3. So that tells us the period of this function here is equal to 2 pi over our b value, which is 3. Or if you put it over a common denominator of 12, we can see that this is going to be equal to 8 pi over 12. So this means we need to keep adding this period to our two solutions over here until we are outside of our domain. That's when we would stop. So if we do that to our pi over 12, the next solution would be 9 pi over 12. Which is still within the domain. And then adding another 8 pi over 12 would give us 17 pi over 12, which is again still in the domain. And then adding one more 8 pi over 12 would give us 25 pi over 12, but that is greater than 2 pi. So this is when we would stop, and that is not in our domain. Next, we do the same thing. 7 pi over 12 plus 8 pi over 12 would give us 15 pi over 12. And then next one would be 23 pi over 12, which is just under 2 pi. And we can see that if we add another 8 pi over 12, it would be outside of our domain. And this makes sense because our b value is 3, which means usually we would have two solutions within full rotation. So if we compress our graph horizontally by a factor of 3, we would have 3 times the solution, which is why we have a total of 6 solutions in this domain. So let's just go ahead and write it out once more. So our solutions to this equation here would be x is equal to pi over 12, 7 pi over 12, 9 pi over 12, 15 pi over 12, 17 pi over 12, and finally 23 pi over 12. Now for our next problem, we can see that immediately we have a double angle here. So that tells us we're most likely going to be using our double angle identity. So let's take a look to see if that works. Sine 2x is equal to 2 sine x cos x. And that is equal to the right-hand side, which is cos x. Now, seeing cos x on both sides might tempt you to divide both sides by cosine x. But we don't want to do that with an equation because by doing that, we're going to lose the cos x is equal to 0 solution. So instead of dividing both sides by cos x, we're going to move everything to one side. So that means we get 2 sine x cos x minus cos x is equal to 0. Now we're going to factor out our cosine x. So we get cos x multiplied by 2 sine x minus 1 is equal to 0. And now because we have two factors multiplied together to be equal to 0, we're going to set each of them to equal to 0. So we get cos x equals 0, or we get 2 sine x is equal to 1. And then isolating sine x gives us sine x is equal to 1/2. Now from this first equation, we get x is equal to pi over 2 or 3 pi over 2. And those would be the two solutions within this domain here. Now for our second equation, this would have a reference angle xr of pi over 6. So since sine is positive, we would be in quadrant 1 or quadrant 2, which would give us the solutions x is equal to pi over 6 or 5 pi over 6. So then now putting everything together, we would have 4 solutions within our domain, and they are x is equal to pi over 2 or 3 pi over 2 or pi over 6 or 5 pi over 6. Now our third equation looks a little bit more complicated. Notice how we have both sine x and cos x. Not only that, but our cosine x is squared. The fact that it's squared tells us that we're most likely dealing with a quadratic structure. However, we can't do anything right now because this one is cosine x and this one is sine x. So that means we want to change our cos squared x to sine squared x. And the way to easily do that is using our Pythagorean identity, where sine squared x plus cos squared x is equal to 1. And if we were to isolate our cos squared x, we get this is equal to 1 minus sine squared x. So we're going to go ahead and do that substitution. So we get 3 times, and then in bracket, we have 1 minus sine squared x minus whatever is left, which is 4 sine x plus 1 is equal to 0. Now distributing our 3 is going to give us 3 minus 3 sine squared x minus 4 sine x plus 1 is equal to 0. And now we're just going to combine like terms, and I'm going to divide both sides by -1, so our leading coefficient here is positive. So that gives us 3 sine squared x plus 4 sine x minus 4 is equal to 0. And now we have a quadratic equation. And if you have trouble seeing that, go ahead and do a substitution where you let a be equal to sine x. And you will see that this is just 3a squared plus 4a minus 4. So now factoring this, we're going to get 3 sine x minus 2 and sine x plus 2. And this is equal to 0. Again, setting each factor to 0 is going to give us sine x is equal to 2 over 3, or sine x is equal to -2. But we know that our sine curve looks something like this. And it's always going to be oscillating between -1 and +1. So that means sine x equals -2 is going to have no solution. Now our other equation of sine x is equal to 2 over 3, that is not a special triangle. So instead of putting it into a calculator, we're just going to leave it in exact form. So we're going to take arc sine of both sides, which means we get x is equal to arc sine of 2 over 3. In fact, that would be our reference angle. And now because sine x is a positive number, we would have a solution in quadrant 1 and a solution in quadrant 2, which means we get x is equal to arc sine of 2 over 3. So this is the solution in quadrant 1. Or the solution in quadrant 2 is going to be pi minus this reference angle. So these would be our two solutions in the domain 0 to 2 pi. And now for our last question, we've added an e to the x in front. So don't worry, we're just going to go ahead and factor that out. So we get e to the x multiplied by cos x minus sine x is equal to 0. And now we have two factors multiplied together to be equal to 0, which means we would set each of them to be equal to 0. So we get e to the x is equal to 0, or we have cos x minus sine x is equal to 0. Now the second equation requires a little bit more manipulation, so we're going to move sine x over to the other side. So we get cos x is equal to sine x, and we can divide both sides by cos x and end up with 1 is equal to tangent x, and this is using our quotient identity. Tan x is equal to 1 is one of our special triangles. It's the 1, 1, root 2. So that means our reference angle, XR, is going to be equal to pi over 4. And tangent x being positive, meaning we're going to be either in quadrant 1 or quadrant 3. So notice how for this particular question, we are not given a domain. And since we're not given a domain, that means we need to find the general solution. So the general solution for tan x is equal to 1 is going to be x is equal to pi over 4 plus n pi, where n is an integer. And this is because the solution in quadrant 3 is going to be exactly pi units away from the solution in quadrant 1. Now for our first equation, which is e to the x is equal to 0, e to the x is an increasing function with an asymptote at y is equal to 0. So e to the x is never going to be 0. So therefore, this one has no solution. So our final answer to this equation here is just going to be this part over here. And now let's do a quick recap of everything that we covered in this video. Today, we used trig identities to tackle equations that weren't solvable at first glance. We saw how identities can pop up in these equations and help us to simplify and solve the equation algebraically. We also saw how trigonometry isn't exclusively its own unit. It can be mixed up with other math topics you've encountered before to form a more complicated problem. And now, it is your turn to give this a try. Can you solve the equation on the screen here? This one can be a little tough. But here's a hint. If you get stuck, go check out the intermediate level video of sum and difference identity, and that should give you a hint on where to start. And if you find the solution, make sure to leave it in the comments below and let us know if you'd like to see more content on solving trig equations in the future. That's it for this video. If you found it helpful, remember to hit that like and subscribe. And if there's a topic you'd like us to cover, make sure to drop it in the comments.